Okay, there's only one thing to finish up with respect to the encapsulation demonstration that we did all last week, and that's unique to C. What I left here was a to-do to actually free up the book and everything that's associated with it. Now, just to make sure that we're actually freeing it up, what I want to do is I want to take a pulse by running valgrind on this. So I'm going to go ahead and compile everything together here, book.c, and I moved everything over to book demo so that we can move on to the next thing here. And when I post it, it'll be book demo. But remember that you use the -G flag in order to retain all of the metadata about your code so that valgrind can produce a report. I'll also include the wall flag there. Now, when I run this, of course, we get the same answers as before. We've processed all the books. There's the oldest book. There's the newest book. Actually, before we do this, let's make sure that... Oh, okay. Before we do that, let's go ahead and fix this part of it. That's another thing that I forgot about because I didn't put a to-do there. Right? To-do, fix this. All right, so back it up a little bit here. Now, why is this wrong? Well, it's a static array, right? And if I went over to my data over here and I added something, right? So something and then, I don't know, Anne of Avonlea. There we go. Right, and then the rest of all that, right? Then would that original code where we hard-coded 42 books work anymore? No. If I went back and I deleted some books, right, then it would work even less. So none of these things are going to work if we hard-code a value like that. So what I want to do is I want to come back and make it so that this is not a static variable. This is not on this stack. Instead, we're going to change this into a dynamic one, dynamic array. And so it would look very much like what you've done before, right? Books, star, right? And then it's going to be a call to malloc. So book, star, malloc. And then how big do you want it? Well, how big is one book? How many bytes does one book take? How many bytes does an integer take? Size of int, right? Well, you can do the same trick here. Compilers are dumb, but they're smart enough to be able to count up the number of bytes if you've declared something already. Okay? That's making sure that this works. Good. We're good. Okay? All right. So how many of them do you want? Well, 42. Right? Now I'm back at the same problem where I'm hard coding 42 all over the place. So suggestions on how we can go about doing this. I want to know how many records are in that file that I've opened or I'm about to open or whatever, right? How have you done it in your hack this last week and that's due tonight? Right? So you want to read all the files, all the lines in. Well, you go through it and you count up the number of lines first. -1. Why -1? Because of the not the null terminating character in this case, but because of the header data at the top there. So let's go ahead and do that. Let's go ahead and read through, right, and count up the number of lines before we read it a second time. And so I'm going to go ahead and copy and paste this while loop up here, right? Actually, after that, and then I will copy and paste this get down here to get the next line, right? There we go. And I can now have a function here, or not a function, but a variable called numbooks. Right? I'll initialize that to 0 because I haven't read any books yet. And then for each line, I will say numbooks, ++. Okay? And before I do anything else, let's go ahead and make sure that this is just some ad hoc testing here. I read %d lines, right? And the line, and that's numbooks. Actually, it's not the number of lines. I read the number book records. Read blank book records. All right. Now let's make sure that this is correct because I'm wasting the first line up here already, and then I'm setting myself up for the first iteration of the while loop by reading that second line. That's why I'm adding ++ every single time. And so let's see if it works. All right. So GCC. All right. Oops, I've redeclared numbooks, so let me come down here and get rid of that one. There we go. And I want to know if I'm processing the book records correctly up above now instead of down here, so I'll get rid of that as well. A.out. And I haven't read them. We'll talk about that here in a second. All I'm doing is making sure, ad hoc testing, that I got 42 records out of that. Good? All right. Now comes the problem, right? I've destroyed all my data somehow. You tell me why. All right? Actually, before we do that, let's go ahead and finish this out. Numbooks. right? Num books. There we go. Okay. There, and I can get rid of my ad hoc debug testing right there. Right? And I can get rid of my to-do because I've done it. So I go through the file once. Where is the pointer at that point at the end of the file? It's at the end of the file, right? So what do I need to do? I need to rewind it so that I come back up to the top so I can read everything again. Right? One way that you could do that is by closing the file and opening it back up, and it'll automatically start at the beginning again. Right? I don't want to close it. I want to use one of those value-added functions or whatever I called it before. Right? Remember that all this nomenclature comes from those big giant tape decks from the 60s or 70s, right? And you can seek, you can file seek forward, or you can rewind all the way to the beginning of the tape deck. And so that's what I'm going to do. I'm going to go say rewind, and I've been reading from F, I believe, right? Yeah, F, okay? Now be careful, because I've rewound it all the way to the beginning. Where is my file pointer? It's pointing to that same line up there that I need to ignore, that I need to burn. And so what I'm going to do is I'm going to grab this up here, and I'm going to repeat it down here, except that I'm not going to redeclare that function there. Why am I doing it twice? I'm doing it once to burn that first line. Burn, ignore is what I'm talking about. Ignore the first line. Then why am I doing it a second time here? To set up the first iteration of the while loop, right? ... And that's what I'm doing here for the next while loop, okay? Let's see if it works. Let's go ahead and clear this out. GCC, run it. There we go. So artificial condition is the last one. All the way up at the top is Anne of Green Gables, and I believe that those are the same ones that we've been working with this entire time. Anne of Green Gables at the top, artificial condition at the bottom. Good? All right. Now that we've fixed that, let's go ahead and run it through Valgrind like I wanted to at the beginning, and make sure that, what we're going to do is we're going to have a baseline. How much memory are we leaking by not cleaning it up, right? So Valgrind, Valgrind, no dot, Valgrind, and then out. Oops, got to type it correctly, out. There we go. All right, so definitely lost and indirectly lost, right? I've got about 6K here that I'm losing, right? Now that doesn't seem like a lot, right? And it's not, but that's because my data, I've only got 42 books. What if I had millions of books, right? Well, what if I had the entire database of goodreads.com itself, right? Then that starts to add up and I'm leaking memory. What if this is a program that was running on the server 24/7, right? Now I'm leaking memory everywhere. So I want to make sure that I'm cleaning up, okay? So the first thing I notice here is this malloc, right? Well, that malloc needs to be cleaned up, right? Because I've created now 42 books. And so what I need to do is I need to come down here, and after I'm all done, I will free up the books, okay? GCC this again, and remember it's 36 and 24 respectively. What did we clean up? That 36, right? 36 divided 3600, whatever it was, divided by 42. That'll tell you how many bytes are in each one of those books. How am I? I'd say that this is indirectly losing. How am I still losing memory here? Right? Remember, what do we have in a book? We have a pointer to a string for the title, last name, first name, ISBN, publisher, and date read. We're doing dates differently here. This is the structure. So title, ISBN, publisher, and then, so I count 3 there. And then over here in the person structure, we've got 2 more strings. So I count 5 strings there total. In fact, if you scroll up here, you'll see 42 blocks definitely lost in record at malloc at init book on line 33, on line 31, on line 23. Right. So where are these? Let's start at the top. Let's see, line 33. So what are we doing on line 33? We are declaring the first name, right? We're creating memory for the first name. What are we doing on line 31? We're doing the last name, right? So those need to be cleaned up, right? And if you follow all of these 5, right? There are 5 blocks here, 5 records, right? How many strings did I observe? 3 in one class and 5, or not class, but structure, and 2 in another, right? That corresponds to those 5 strings. So what we have to do is we have to implement this free book function that I said that we would do later. And let's see if that's enough, okay? All right, so what needs to be freed up with respect to a book? Well, you need to free up the title. So free b title. Why did I use an arrow there? Because I have a pointer. Free b's ISBN. Free b's, and here, let's go ahead and split screen this. Nope, split screen this. Split screen this. There we go. All right, finally. And what else is, so there's the ISBN publisher. Right? That takes care of the three in the book structure. Now the book has a author structure here. So free b's person, which is author, dot or arrow here for the first name and the last name. Which one is it going to be here? Remember that person is a regular old structure. We don't have a pointer here. We have a pointer with respect to B, but once we get to B, right, it's author. Well, that's a regular old structure. So we would use the dot operator and free that up. And I'll likewise free up the last name. All right, last name. There we go. What if I were to free B right here? Careful. Remember, memory management, one of the things you have to ask yourself is, who's responsible for this memory? Okay. Now the book itself, where was that created? It was created way up here on the line that we just wrote, right? And in fact, 42 of those books were created right here. So does the book own that memory? Or, I mean, this is an array of books, right? So it doesn't belong to each individual book, right? It belongs to wherever you declared this. And in this case, it's going to be main, right? So it's main's responsibility to clean up those books like we already did. If I did this, then basically what would end up happening is you would end up like freeing up like one of the middle books. And you can't do that, right? When you free up that initial book, it would end up freeing up the entire array of books because the pointer is not to the first book. Technically, it's to the start of the array, right? And so if you free this up, it ends up freeing up all 42 books before you've had a chance to clean up those other 5 strings of all the other 41 books remaining. So we're not going to do that, right? You should have a return statement here, even if it's not returning anything. Right? All right, let's go ahead and recompile, and let's run valgrind again to make sure that everything, we have a clean bill of health here. And oops, what did I forget to do? Yeah, I never even actually called the functions, right? So let's go ahead and actually call that function here. Right here, for each book, we will say free book, right? In B sub I. Careful. Or books, sorry, books, right? Books itself is a pointer to an array of books, all these books over here. When I go books of I, then I'm getting one of them, which is a regular old structure. This function requires a pointer to that function, to that. So what do I do in front? Ampersand. GCC. Run this again, and there we go. All heap usage, all freed. 258 allocations, 258 frees, and 14,000 bytes, and are all free. There's no errors, there's no memory leaks, nothing. At least that valgrind can detect. Okay. 258 allocations, 42 times 5. I think that there were 210. All right, so where are the others coming from? I'm not sure. Oh, I know. Every time we call print string or something, right? Then we are freeing it up. And so I could get rid of those and count those up. But you see it's about on the level. Right? That's the number of allocations and deallocations that I would have expected. Right? All right. Any questions on encapsulation or any of the exercises that we've done over the last week? By the way, over here, do we have to clean up the books? Is there a free function in Java? No, because Java has automated garbage collection. It takes care of everything for us. Right? So there's no concept of a destructor. C++ has destructors. Those are the two only languages, maybe Rust, I'm not sure. Those are the 2 languages that I know of where you're having to do manual memory management for yourself. Right? Otherwise, most of the other programming languages take care of it for you. Inefficiently, efficiently, depends. All right, let's go ahead and get rid of all that. And I will post all of this code along with the notes at the end of the day. But let me go ahead and open up the new demo here. And let me go ahead and go on to the next topic here. Just wanted to finish up that so that we had all of the moving pieces. Right. Now let's talk about recursion. Right. Well, first of all, what is recursion? Yeah, go ahead.
Is it like a function that calls itself?
Yeah, okay. That's the straightforward answer. Let's go ahead and ask Google, though. Right? If you've seen this joke before, right? What is recursion? Right. All right, well, okay. Now the AI has screwed up their joke. Recursion.
Wikipedia page say, like, see recursion.
Yeah, there we go. There. Did you mean recursion? All right. Now the joke works, right? So click on that. Did you mean recursion? Did you mean recursion, right? Recursion is any actual self-reference. And in this case, we've got a function that references itself. So as a challenge here, let's go ahead and print out a countdown without a loop, right? In other words, we're going to print out 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and then blast off when we get down to 0. And we're not going to I'm not going to allow you to use any loop. And I'm not going to allow you to use any hard coding. So you can't just have like 11 print statements there, right? Can you do it? All right. What do you have left? You have functions. All right. So let me go ahead and create a function here called print blast off. Let's call it blast off, or count. Let's call it countdown because that's what it does. Countdown. All right. It doesn't matter what we return. I'll just keep this as a void function. And let's suppose that it takes n here. That is the number that I'm counting down. Right. Now, I could just print this out, print f, %d, end the line, right, n. And I could, of course, do this once, call countdown on 10, okay? Now, if I did this, demo.c, a.out, it's just going to do it once. How do I get it to do it multiple times? Well, I could go countdown 9, 8, 7, 6, 5, 4, 3, 2, 1. Again, you're not allowed to hard code these values, right? But that kind of, I don't have to just call countdown here. I could call countdown because it's a function anywhere in my code. Right? Where else could I call it? Inside countdown. Countdown. Now 9, 8, 7, 6, 5, 4, 3, 2, 1. But I've already got n here. Why don't I just go n minus 1? So if this receives the value 10, then it'll print out 10, and then it'll decrement 10 now that we're down to 9. And then it'll call the function again. Right? Then it'll call the function again on 8, 7, 6, 5, 4, 3, 2, 1. If I just did it right now, what's going to happen? Yeah, infinite loop. It's just going to keep going negative. What's going to happen in a matter of seconds here? In fact, it just did. Segmentation fault. I didn't have any memory management. I didn't call malloc or anything. What's going on here? Let me go ahead and take this, and let's go ahead and go to Python tutor, C. Right. So recursion, as you already said, is a function that calls itself. So basically what you're doing is you are creating a loop, right? Because obviously this takes forever. This is an infinite loop. But to keep track of the loop, you are basically abusing the call stack, okay? So here's the call stack, and it got stuck in an infinite loop, and so that's why it took so long there. But countdown, main calls countdown, right? And it's not as pretty anymore because it errored out here. There's the stopped after 245 steps here. But you can see that we've got those things called stack frames, right? And countdown 10, right? Then countdown called itself again, 9. Right? 8, 7, 6, 5, 4, 3, 2, 1. And then eventually when I got to 0, I wanted to print blast off and then stop, but it just kept going. Kept going, kept going, kept going, right? Eventually what happens to that poor little stack? What happened over here? After 261,000 calls and some change, what happened to that stack? Stack frame on top of stack frame on top of stack frame until it gets filled up, and then the next very next function call, what happens there? Stack, overflow, right? So I'm abusing the call stack here, and I shouldn't. I shouldn't do that to begin with. But let's go ahead and fix that problem now. Right? I want to add in what's called a base case. If I get down to 0, then I don't want to recurse. I don't want to call this function again. What do I want to do? I want to print out blast off because I'm done. Right? And then I'll return. Okay? Now let's go ahead and run this. There. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, blast off. Now if you ran this through the Python tutor again over here, you would see that it would actually stop here at, where is it, 0, right? We would have countdown 0, but then it would have started returning to the call to the calling function. This stack frame, what is that called when it is taken off the top of the stack? What are those two operations? You push onto the top of the stack and you pop, right? That would have popped off, popped until you got back down to main eventually, all right? So that's what recursion is. It's basically a function calling itself. Right? In general, recursion is all over the place, not just in coding, but it's anything that references itself, right? In mathematics, right? You have what are called fractals. Fractals. You've seen fractals before, right? Self-similar stuff. I don't know. Fractal art is usually what you see. It's just images, right? There. It's probably the Mandelbrot set is the most common, right there. And let's go ahead and Sierpinski triangle. This one's is much easier to understand. Let's go ahead and take that one. That's kind of ugly. Let's take that one instead. There we go. So the Sierpinski triangle is a triangle, and then you split it into 4 triangles, 1, 2, 3, 4, and then you remove the middle one. Right? Then you recurse. You do that again for each one of the triangles up top and bottom. Right? If I took out art here, Sierpinski triangle, do I have a image that shows? There we go. So here's the first iteration. You start out with a triangle. B, you remove the middle triangle after splitting it up into 4 triangles. Then you do the exact same thing, C, over here on those 3 triangles. Then those, how many triangles now? 9 triangles. And then 27 triangles. And then 81 triangles. What's the pattern there? Powers of 3, right? Because you end up with 3 triangles, and then you end up with 3 triangles, gives you 3 more triangles each. So that's 9, right? So it's going to be 3 to the n, right? Okay? You also see it in mathematics in things like, say, the Fibonacci sequence. And this is always trotted out when somebody introduces recursion. And I'm not going to be any different, but I'm going to take a different point of view here. The Fibonacci sequence is a perfect bad example. Right? It's a perfect example of what the bad stuff, of the drawbacks to recursion and why you would not want to do recursion. Right? And we're going to see that here in a moment. Before we see that, let's go ahead and remind ourselves of what the Fibonacci sequence is. Right? Anybody not seen the Fibonacci sequence before in math? Right? No? Never seen it? Okay, good. Then this will be brand new to you. Right? So the Fibonacci sequence is if n is 1 or n is 2, then the values are 1. Otherwise, what you do is you take the 2 previous values and then you add them together, and that's the next value. So, for example, if you start out with 1, 1, those are the base cases, right? There we go. There's 1, 1. Then the next number is the 2 previous values in the sequence. So 1 plus 1 is 2. Now the next one is the previous 2 values in the sequence. So 1 plus 2 is 3. And then that's the pattern. 3 plus 2 is going to be 5, right? Then 8. Now what? 13. 13 plus 8 is going to be 21. 21 plus 13 is going to be 34, right? 55, 89. Let's go one more there. 89 plus 55 is going to be 144. Is that right? 89, come on, 130, 144. Yeah, that's right. Right? And it's infinite, right? It goes on forever. L dots. There we go. It's an infinite sequence there. Okay. All right. So in coding, a function is going to be recursive if it makes 1 or more calls to itself, like our countdown function. Okay. All right. So Fibonacci is going to be our prime example that we're going to start out with here. I guess we started out with the countdown example, but this is going to be our second example. Just look at the definition. Right? It lends itself to an easy chunk of code. If n is equal to 1, then return 1. If n is equal to 2, then return 1. Otherwise, make it 2 recursive calls, one on n minus 1 and one on n minus 2, and then sum those together, and that's your return value. Okay? So let's go ahead and get rid of this countdown here and call it Fibonacci instead. Right? And we'll take n here. Right? And if our base cases are different here, if n is equal to 1 or n is equal to 2, then we'll go ahead and return what? The base cases were 1. So I'll change the return type here to n as well. Otherwise, else, what do? We make one recursive call on Fibonacci of n minus 1, another recursive call on Fibonacci of n minus 2, and return their sum. So int a is equal to Fibonacci of n minus 1. Int b is going to be Fibonacci of n minus 2. And then I'll return a plus b. Now I separated those two out. Of course, you could not have to create 2 new variables here, and you can just simply say return Fibonacci of n minus 1 plus Fibonacci of n minus 2. And guess what? It looks exactly like the mathematical expression over here, right? But I've got a purpose with creating those 2 variables that we'll come back to later. Right? So I'm going to do it this way. Let's make sure that it works. I'm going to read in n from the command line. Right? Int n is equal to a to I of argv sub 1. Right? And to do error handling here, if argc is not equal to 2, why 2 again in C? Because of the program's name is the first one, right? Then printf error provide n whatever, and then exit on them. Otherwise, I'll go ahead and take that as a command line argument, and then I will compute the result, Fibonacci of n, and then printf fib of %d is equal to %d and the line. So this will be n and the result. Okay. All I'm doing is making 2 recursive calls, except that I've got a base case up here. Remember, you need a base case, otherwise you will infinitely recurse, right? You don't want, it's infinite one way, right? But it's not infinite both ways, okay? You don't want it to, what happens when n is less than 1, right? It's not defined. So you can actually incorporate that up here. If n is less than 1, I don't know, printf error. Actually, we shouldn't be printing anything in this. What should we return? Some value that is definitely not part of the sequence, -1, right? And then we can incorporate this into an else if, right? So that if you call it on, we'll find out here in a second what it looks like, but gcc demo.c, right, a.out, right, I need to provide n. Let's try the base cases first. 1, 1, 2, 1, 3, 2, 4, 5, 6, 7. Does it look correct to you? Right. Let's just jump ahead here to, what would it be? No, that's too far. 12? There we go, 12. That was the last one I did by hand over here, 144. Right. What would happen if you did negative values, -10? Well, we're catching that error value and saying -1. Okay. If I didn't, what would happen? What if I didn't have this? Copy this and get rid of it. Save this. GCC. What's it gonna happen here now? Segmentation fault immediately, right? Why? Infinite recursion, right? That filled up the stack, and then you had stack overflow. Why was it so much faster here? Because remember I/O, input output. That is your bottleneck in all of computing. Before, with the countdown, we were actually printing stuff out. So that took a while to print out, and then it died, right? Here, I'm not printing anything out, so it's allowed to immediately fail, right? Okay, so let's go ahead and restore that. Great, GCC, run this again, and run, what was it, 12? There. What would be next? 13, let's just go one more there. 233, so 89 plus 144, that looks like it works. What's the, I don't know, 40th Fibonacci number? Is that correct? I don't know. Let's go. How can we find out? Well, from alpha, right? So Fibonacci of, say, 40, or you can read his biography there, right? There we go. 102,334. Oops. 102,334,155. Looks like it works to me. Although, did you notice? It just took a little bit longer. Like just a half a second longer. Let's go ahead and kick it up to 50. Actually, even just 45. 45, sorry. There we go. Now it's taking noticeably longer, right? Okay, but we still got an answer. I don't know, is that correct still? Let's go ahead and ask Wolfram Alpha here. Fibonacci of 45, right? And is that equal to, is that true? Yes, it's true, right? All right, so we got there. What if I went up to 50? How long do you think I should wait for this? I'll go ahead and let it go. Let's understand why it's taking so much longer for these larger numbers. First of all, is 50 that much larger than 12? No, right? It's only 4 times as big. Here's what's actually happening in the recursive calls. And this one is simplified for Fibonacci of 5, okay? So Fibonacci of 5 makes 2 recursive calls, one to Fibonacci of 4, one to Fibonacci of 3. Fibonacci of 4 makes 2 recursive calls to 3 and 2. 3 makes 2 recursive calls, and each one of those makes 2 recursive calls, 2 recursive calls, 2 recursive calls. How many times do we end up calling Fibonacci of 0? I don't have any writing utensils up here, so let's just put it up here, right? And here's our observations. Fibonacci of 5 makes how many calls of Fibonacci of 4? Let's say. There, it finally did it, but we'll come back to that here in a second. So there's one call to Fibonacci of 5, right? Sorry, Fibonacci of 5, right? Has one call, right? Fibonacci of 4 is equal to, how many times do I call 4 there? I see 1, okay? How many times do I call Fibonacci of 3? I count 1, 2, right? Good. How many times do we call Fibonacci of 2? I count 1, 2, 3, all right? Now that I'm writing them down, do you kind of see what's going on here? Fibonacci of 1. How many times do I call Fibonacci of 1? I see 1, 2, 3, 4, 5. All right? 5. All right. So, how many recursive calls am I making in total? You'd sum them all up. But what is the sequence right here? Fibonacci sequence, right? 1, 1, 2, 3, 5. That's how many times I'm calling them. So in other words, if I want Fibonacci of 55, or what did I do, 50, I think? There we go. It's that many function calls. Right? So how many is that? That's whatever. Right? I'm doing 12.5 billion operations. Right? So that's why it took like maybe a minute or so to do it. We didn't actually get a correct answer. Why? What value is that? That's more than an integer, right? How big of an integer? How big of a value can we store in an integer? 2.147 billion, something like that, right? And that's 12 billion. We're not going to be able to store that, but we were able to compute it, just not correctly, right? What if I went up to 100? Now, 50 took me 1 minute, and this is several orders of magnitude more, right? Let's just go ahead and try it over here. Now, they're going to be able to Fibonacci of 100. Hey, there. Let's use that. There we go. So it's that many calls. How big is that? Call them millions, billions, trillions, quadrillions, quintillions. 354 quintillion operations, right? Let's assume that we've got a really fast, powerful computer here, right? How many floating point operations per second do you want to go? If you did, say, what, 6? That's 1,000,000 floating point operations per second. That's megahertz, right? Let's go up a little bit more, though, because everybody measures in gigahertz now, right? That is 1 billion floating point operations per second. Let's go up even further. What if you wanted to do terahertz or whatever, right? Now you're on a cluster or something, and you want to do 1 trillion operations per second. That's how many seconds it would take to execute this. So let's ask Wolfram Alpha to tell us seconds to minutes. Okay, there. 4,100 days, right? That's 11 years, Gregorian years, right? So 11.22 average Gregorian years. Should I be waiting for this to execute? No. How was Wolfram Alpha able to do it? They didn't use recursion. At least they didn't use dumb, naive recursion as I'm using right now. Instead, what did they do? They used a simple loop and kept track of 2 variables, right? It started out, the variables started out as 1, 1, and then they added them up into a temporary variable, and then they moved these variables over and over, right? And all they had to do was 100 operations then, because if you want Fibonacci of 100, then you just need to execute it that loop 100 times, keeping track of 2 variables, right? So that's why I love this example. Right? It's a perfect bad example, right? And it's the one that's always trotted out whenever somebody introduces recursion. If you've seen recursion before, have you always seen the Fibonacci, right? But you've never maybe looked at it in terms of, no, this is terrible. We shouldn't be doing this, right? Because of this repeated work. You called Fibonacci of 3 twice. Why? You could have just called it once and then stored the result. We call that caching. And it's a solution that we're going to look at here in a moment called memoization. No, I'm not mispronouncing that. It's not memorization, it's memoization, right? But before we do that, and we'll probably get to it next time, some tips on designing recursive functions. Every recursive function has to have at least one or more base cases with no further recursion performed, right? Some base cases may be used for error handling, right? You need base cases generally come first in the function, right? Anything else I wanted to say about that? No, one or more base cases, right? And then you make one or more recursive calls that must make progress towards those base conditions. This all sounds very, very familiar, right? You have a starting point for a loop. That is your initial call to the recursive function. You have a base case, that's your termination condition that you don't do anymore. Then you also need to make some progress towards one of those base conditions. Those 3 things are what? Those are the 3 parts of a loop. Right? So recursion is nothing more than thinking about a loop, but thinking about it in terms of function calls rather than a for loop or a while loop. Right? And then finally, again, the initialization. You have to make an initial call to the recursive function to get everything kicked off. Okay. In fact, sometimes when you do recursive functions, you'll have 2 versions of them, the recursive version and the non-recursive version. And the non-recursive version is the one that gets everything kicked off. Do operation. Then the do operation actually calls the recursive do operation because it handles all the logistics for, well, how do I initialize this function, right? So why do we cover recursion? Well, there is some good to it, right? It's not all bad, right? It can be useful or good, right? In fact, you're going to see many divide and conquer algorithms that are presented recursively because that's what divide and conquer is, right? Divide and conquer, Sun Tzu, that you take an army and you divide the army, you defeat half the army, and then that leaves the other half for you, right? You don't have the numbers to defeat the entire army at once, so you divide them, then you conquer each one separately, right? Do divide forces. Same thing with problem solving. This problem is too big. I don't know how to handle it. So what I'll do is I'll cut it in half, and I'll solve it. Or I'll solve that half. Well, I still don't know how to solve that half. So what I'll do is I'll cut it in half again. cut it in half, cut it in half, cut it in half, until it gets down to something that is trivially solvable, right? For example, sorting. We're going to look at a quicksort algorithm later on or merge sort, depending on which one we look at. I don't know how to sort these 10 things, so let's go ahead and just focus on these first 5 over here. I don't know how to sort those either, so we'll look at 2 of them. I don't know how to sort those, so we'll look at 1 of them. Do you know how to sort one thing? Yeah, it's just by itself. You're done, right? It's trivially solved, right? It's a good way to think inductively. You're not in 235 yet, but you will be next semester. And one of the proof techniques that you'll look at is induction. And induction is nothing more than another restatement of recursion, right? Where I don't know how to prove this thing, so let's look at a smaller version of it. I don't know how to prove that, so let's look at a smaller version of it until you get down to a base case. And then you can show that if you can show that the base case implies the next case, implies the next case, then this unrolling, there's your proof, right? It's an inductive proof. There are many languages out there where you are forced to do this. They're all called functional programming languages, like Haskell, Scheme, and Lisp. In some of these languages, you can't even declare a variable, right? These languages do not have for loops or while loops or any loops at all, right? Instead, they're functional programming languages, and everything is done recursively, right? There's a great quote by Bjorn Stroustrup, the inventor of C++. He said that there are only 2 types of languages. The ones that everybody hates and the ones that nobody uses. And I'll tell you right now that these are the ones that nobody uses. Some people actually love them. Some people are huge functional programming fanboys, and I'm not one of them, right? Recursion can also lead to simple, clean, or beautiful code that is easily understood. Right? I'm putting all those into quotes because how would you characterize these ideas? One person's simple is another person's complicated. One person's beautiful is another person's ugly. These are all subjective standards, right? When we get into the bad, that's when it's all objective, right? You risk overflowing your stack with runaway recursion, right? As we already saw, stack overflow because you're going too deep. In fact, you're only able to go 4 megabytes deep, however divided by however many stack frames you're doing, right? So you a loop, if you rewrote it as just a simple loop, right, then you could probably calculate very large things just using a simple loop because you're not using too much memory. But if you are using a stack and abusing that stack to do your loops for you, then you can't do all that much, right? Even if it is an runaway infinite, again, you're still abusing the stack, and which is limited. Right? Most or all recursive functions can always be rewritten as a regular old loop anyway. Right? Fibonacci, right? You don't write it recursively. You would write it, well, you don't write it at all because who cares about it. But if you had to write it, like in an interview or something, you would write it as a loop with you keeping track of 2 variables. Right? You risk a naive exponential blow up to a simple problem, right? Like this over here. Right? This is this tree is an exponentially sized growing tree, right? And you're going to end up doing an exponential amount of work. It's going to take you 11 years to do Fibonacci of 100, right? And we don't have time for that, right? So what we're going to look at next time is how to eliminate recursion, right? Sure, you go ahead and come up with a nice way of thinking about a problem, a nice way of solving a problem using recursion, but then what we're going to do is we're going to use a technique called memoization to get rid of it, right? Like I said before, I separated these out into 2 calls because I'm not going to actually make the calls. What I'm going to do is I'm going to look it up. If Fibonacci of n minus 1 has already been computed, right? In other words, it's been stored for me, then use it, right? Else, all right, it hasn't been computed. So what we'll do is we'll make the recursive call, and then store it, or this is called caching it, cache it. Or cache. We just said cache it. Why do you want to cache it? Because next time you ask for it, then it's going to be there, and you don't have to make that recursive call. Right? So how are we going to do that? How are we going to create a cache in order to store stuff? Well, that's what arrays are for. Right? And so we're going to create an array to store the stuff so that we don't have to do it anymore. Right? And we don't have time to get started, but that's what we'll do next time. Any questions? All right, so how many people have not seen recursion before today? All right, everybody's seen it before? All right, good. It positively? Yeah, somewhat positive. Okay, negatively ever? Like, no, you shouldn't be doing this. No? Okay, well then this is your first time. By the way, there are some style guides. For example, NASA forbids all recursive functions in any of their code base because they're dealing with embedded systems all the time. Embedded systems are going to have extremely limited memory, extremely limited stack space. They can't afford runaway recursion or even shallow recursion, so they don't even allow it. Right? Some programming languages don't support or haven't supported in their history recursion, and then they added it for whatever reason. Right? Usually, you can always take a recursive function and just rewrite it or simulate a stack instead of using the call stack to do your work for you. Right? So there's always a way around it, right? And we're going to look at one way around it next time. All right, see you then. Oh, before we go, for those online, remember that there is a student advisory board meeting, or a student advisory panel, I guess this is what it's called, on Wednesday from like 11 to 1, I think, upstairs, free pizza. Come and talk and tell us what you think. I'll be there because I want the pizza, but you can ask questions of faculty, and you can get your questions answered.